Hello folks, so we're back to do some more work on truss computation. So if you remember last time, about a week ago now, last time we had written a program in differential dataflow, a few programs, but specifically we wrote a program that would try and determine something called the truss decomposition for graph. And what this meant was to try to find essentially levels, integer levels like 0, 1, 2, 3, where an edge lives at level k, let's say. If when you take all of the edges that live at level k or higher, that edge participates in at least k triangles. So this is not just how many triangles in the graph do you participate in. That number could be pretty big, but maybe those other edges that form a triangle with you don't themselves have very many triangles. So these levels are designed to try to tease out which sets of edges mutually have lots of triangles all at the same time. And this is exciting for some reason. I don't personally know, but my guess is that this is a nice and indicative of strong community structure. There's like lots of non-spurious triangles, triples of people who didn't all have to be connected. A, B, and C, where it's easy for A to know a B and for B to know a C, but if A also knows the C, that's a good indication that this is a little stronger collection of people. And the K, like these levels here with the K trusses are stronger and stronger, more and more dense subcommunities. So one theory might be that if you pull out all these little trusses at different levels, then you can sort of scroll around to the progressively more and more tightly knit communities, and then dial that back to more tenuously connected communities, and so on. I'm just making that up, though. But where we left ourselves last time was we had written this nice, this program, let's say, that loads up some data from some files that we have. It tells us that this happens. It creates a new differential data flow here, and from a collection of edges that come in, it orients them correctly from small to large, and runs off and calls this truss method, which I wonder if the tooltip will tell us. Great. It takes a collection of edges and produces a collection of pairs of edges, and it says node, but basically an integer that is the maximum node identifier. So that's the largest number of triangles you can participate in this, however many nodes there are. And we'll look at that in just a moment. But the rest of the code is sort of pulls out some summary statistics telling us how many people are in each level. This count is the level. How many people are in each level, and if we ask to look at the results, then it'll tell us what's going on. I'll show you this running in just a moment. We have to fix it first. And it grinds some data through here. There's a particular experiment that a paper that we were looking at does where they load all the data except for 10,000 edges. This looks terrible. Oh, okay, this is what dead code looks like apparently. Let's just delete it. Oop. For those of you who are about to find out, I have a new keyboard that I'm trying out. It's a mechanical keyboard. It may turn out that this video involves a whole lot of click, click, click sounds, in which case, there's going to be a conflict, because I quite like the keyboard, actually. we'll have to think about that. So the truss computation takes some edges, and if you recall where we ended last time, there were some very clever things that we were going to do involving joins. We're going to have to undo them because there's a bug. It's a bug not in this program, but in the dogs experimental join library that I've been working on. It is defective in certain cases, and I need to fix that. So what I thought I'd do is delete all of that for the moment. We're not going to screw around with that at all. Let me delete the debugging code, and then just quickly catch you up on the much simpler remaining piece of code, the stuff that we got to earlier, and catch everyone up on performance, at least, like how this was performing relative to this recent SIGMOD 2019 paper and its prior work from a few years before. So I'm going to delete a bunch of things, and then we'll try to get it compiling, and once that's actually in the sane state, then I can talk you through what's actually going on. So just as a quick thing, we start by computing triangles outside of iterative computation. So the triangles are going to be interesting. A set of triangles are going to be interesting to us, even without these level annotations along with them. So that happens up here, and then inside the scope we're going to be using them. And another consequence of having this new keyboard is that my typing is yeah, you know, it's typing. We'll get there. So we're gonna just take our set of triangles from outside the scope here, and we need to restructure them just a little bit. Do we need to restructure them a little bit? No, we just need to not mess up the structure. So they're structured at the moment as B, C, A. These tooltips are going to kill me. Turn off this Rust idiocy. How do we bother? Normally it's super easy to turn off the Rust mods because they just yell at you all the time. Well, maybe I should figure this out later. Unless it gets super more annoying. Great, so we have the triangles, bring them in, we do some stuff. We're going to totally ignore all these other crazy things that we wrote down. They're still in the repo, so if you want to check them out, feel free. But conceptually, they're correct, or they seem to be correct conceptually. They're just the supporting logic that does the join computations was not correct. Tidying here. Doobie-doobie-doo. All right, let's see if this builds. So, looks like it. So, if we dive over here, so what we were doing in this algorithm, just to talk you through while that release build goes, we have a collection of edges coming in. These are pairs of integers, pairs of node identifiers, so source and destination. We've already oriented them from large to small, sorry, small to large. So there's a canonical direction on them. We're going to be finding triangles, triples A, B, C from small to large. And we're going to pay a little bit of attention as we do that to make sure that we don't accidentally multiply determine triangles and overcount things. When we start, we're first going to compute these triangles from our collection of edges without thinking at all about restricting edges or levels or any of that junk. And we do this by taking our set of edges, think of them as AB, joining them with a set of edges we might think of as AC. We get out pairs A, B and C, and we only want to keep those for which B is less than C. We would see both cases. We'll see both, for every A, B, C, we'll also see A, C, B, but we don't want that redundancy, so let's just thin it down to those where B is strictly less than C. And we still need to verify at this point that the edge BC actually exists. So we just have a candidate ABC because we see that edges A and B and edges A and C exist. But we need to spin this triple ABC around to have BC as its key over here. And then we semi-join with the edges to restrict our set down to those triples that actually have the three edges. And now we have our triangles. They're written as BCA, which is weird, but that's just how they've come out of the semi-join. We'll just work with that, it's fine. And now our algorithm for this this labeling thing, I'm going to talk through it because we're going to do a slightly different algorithm in a little bit. We're going to try, anyhow. The algorithm says, let's start with all the edges, and we're going to iteratively change some labels around. We're going to start with the presumption, maybe, that like everyone's got a really great label. Like let's start with the biggest possible label everyone could have, and we'll write an iterative computation that progressively decreases the labels. So we're starting really optimistically, and it's going to repeatedly go through and dial back some of that optimism. And the way that works, approximately, is to say that, well, if we've got in our iterative computation a set of labels, these labels are pairs of edge and int, telling us what label we're at, initially very high. What we can do is we can go through each of our triangles and say, what are the current labels for each of the edges, and in particular, what's the minimum label among all of the edges, all of the 3 edges that take part in that triangle, and that tells us at what level this triangle essentially comes into existence. So this triangle doesn't count for any level less than the minimum of the levels of its edges. So if we see a triangle and it's got levels 3, 5, and 7 on it, that means that this contributes nothing to anyone interested in being at levels 4, 5, 6, or 7. It only contributes to counts at level 3, or 2, or 1, or whatever. But if we start talking about levels 4, 5, 6, and beyond, that poor level 3 edge isn't involved in the conversation, and consequently this triangle doesn't come into existence because that edge isn't around. So what we're doing here, these steps, is taking our triangle and sort of fishing out from our labels relation each of the labels, and tracking the minimum value as we go. And that's fun. That's a thing. By the end of it, we get a pair of triangle and label, ABC and label. I'm going to screw up and say label and level sort of interchangeably. It's not great, but that's how it is. The flat map then says, awesome, we've got a label for our triangle. Let's hand that label out to each of the edges. Remember, this is the minimum. It's not their initial label. So we've got a new label for each of the edges. Each of the triangles is going to produce one of these, so that we then go down and say, for each of those edges out there that we've just produced from all of our triangles, let's collect all of the labels from all of the triangles. So these labels have different values. These are the 3, 5, the 7s, but they also have counts. So they show up, and maybe we have 27 occurrences of label 3, which is really exciting, and will certainly put us at level 3, but not necessarily any higher than level 3. So we now need a little bit of logic that walks us through. Given a collection of labels and counts for each of the labels, what is the largest value, k, for which the sum of things greater or equal to k is greater than or equal to k, which is kind of weird. And I think I have that logic written down here. It could be wrong, but that's fine. The gist is roughly that we take our input set of labels, which are sorted from small to large, and we're going to track the total count, and we walk through the labels in reverse order. So we start with the largest label and its count, and we start walking down, looking for the first moment at which the total count that we've achieved so far is bigger than the label that we're looking at now. And there's 2 little bits of logic here to make this correct. As we come into each new label, maybe our total is already bigger than the label we're currently looking at. Like maybe we start looking at we start looking at 3, and we have a count of, I said 27, so let's try 27. What the logic will tell us is say, sweet, that's bigger than 3. We must be at 27, which you might say, whoa, slow down. That's not exactly right, surely. And in fact, it is, because in this little bit of code at least, if we're at this point and total is already equal to 27 before we get to, so we haven't added the 27 count in yet. So before we've gotten to 3, somehow things counted up to 27, and yet we're still running, which means we didn't actually we didn't actually bail out yet. These things weren't bigger than the previous label must have been 28 or greater because we didn't stop previously. And that tells us that, like, well, I don't know, we got a bunch of 27 counts of things bigger than 28. Our label probably 27 at the moment. So we just we ship it and then we bounce out of the code. Now maybe that hasn't happened yet. Maybe we're looking at a label and our count isn't big enough yet, so we bump the total up by the count, and then we look at the total compared to the label again. And at this point, if we have more count than we have the current label, we're good to go with the current label. Now, whether this is correct or not is indeed debatable, but there we have it. At the very end, we need to drop out by saying, if we've run out of labels, we've got this many total triangles that we participate in. Let's just go with that. Again, that total will be smaller than the largest label we saw. So this is still, this is still a regression. We're not cheating here by putting out a really large total. Anyhow, this is the algorithm. Let's see if this build has completed and we can run it just a little bit. Cargo run. And we need to give it a few parameters here. We need to tell it where to find a graph, which will be in projects, datasets. We're going to start with this Facebook graph, which is the teensy-tiniest graph. We're going to give it, we're going to give it a size. And actually, what I want to do is look at its size first to see how many edges it has, because that's going to tell us. So, sorry, we want to basically take the number of edges in the graph, subtract 10,000 from it, so that we do one step that is all of the graph minus 10,000, and then one step that is the remaining 10,000. So, cargo. I have a key bound to space plus command so that I can quickly spotlight things around, and sometimes that gets in the way. Great. So we're going to do 807037 as the number of edges we want to throw in our first batch. We then want to true and true. These are just things that say that, yeah, we want to see the results. We're going to put them to the screen. And we want to clobber the timestamps down to be the batch that they live in as opposed to their default timestamp. We could actually go through and produce about 800,000 distinct updates to which is awesome, and you can totally do this. That's not what we've been asked to do. So let's take a peek and see how this runs. And maybe we'll talk through cutesy optimization that we could do. We'll see. This I've also run this, as it turns out, on my desktop at work, and it goes quite a bit faster there. So this is a 2014 laptop that we're playing around on, and it is not bad, but there are only so many cores on it. It's about it has half the clock frequency of my desktop. And it turns out that when you combine all these things, the desktop is actually about a factor of 10 faster than the laptop, which is pretty cool. That totally changes some of the conclusions that we might reach about its relative performance versus prior work. I'll talk through that in just a moment. Assuming that this takes the amount of time it's taken in the past, it will be about 100 seconds to run, and then an additional 50 seconds to do an update, I think. To do the sort of the 10,000 updatey things. And that goes down if you add more threads, which is nice. So it's sort of cool that we've written this in differential data flow, because it means that we automatically get some benefit from turning on more workers, because we've written a data parallel program instead of just a sequential hunk of code. Sort of curious if I've actually screwed this up and it's let's check while it's running and see if yeah, it's a reasonable amount of memory. It's okay. No, it's still. Sorry, my mental model for how long things. Yeah, okay, cool. So about 100 seconds. It's telling us all of these counts. As before, we topped out at 34, which wasn't the same number that the paper claimed, which was a maximum level of 36. I will look into that at some point, but in any case, unfortunately we don't have a ground truth to work off of here. So there might be a discrepancy, there might be some glitch, like we've thrown away self loops and self loops count as triangle, I don't know. Could be some more stuff. Possibly, I mean, if it actually is the case that 36 exists, we might actually be doing more work than needed because we've taken ourselves all the way down to 34 instead of stopping a bit earlier, but not entirely clear. And now you can see that about 50 seconds later, we did our final update. So 10,000 additional edges and some changes. Someone else at 34, and some other people wobbling around in various places. While we look at the paper, let's turn this on with 2 workers just to get some numbers for that. The paper lives over here. This is a recent SIGMOD paper, 2019. And we're looking at this again because I had asked these folks during their talk, wouldn't it make sense to compare against something like a general incremental compute framework, which was a kind of unfair question, and it wasn't meant to be. I was sincerely interested, but my sense is it probably came across as a bit unfair. So I thought I would try to do the legwork, and I could probably end up failing terribly, and that would be great for everyone. So what we're comparing against at the moment is, or what the points of comparison are this line here, Facebook, which is the tiniest graph. Their paper describes this unit sim algorithm. It describes several, actually, unit sim algorithm, and compares against XH, which is an algorithm from about 5 years ago. The authors, at least one of the authors, worked on, and I guess some variants of it that I'm not sure I understand entirely. So let's. Mostly, what I'm setting up, my mental baseline was, let's see if we can do as well as the 2014 paper. Laptops from 2014. These numbers are probably on a more recent computer, but if we can do approximately as well as this, we'll feel kind of smug, and if we did any better, we would feel especially smug. But we'll learn at least a little bit about where a general purpose compute framework can fit in this space. For example, if it's 100 times slower than purpose-built algorithms from a few years ago, then we've got a lot of ground to recover, but it's not so bad. So, so multiple threads, it takes about 70 seconds just on my laptop, and then an additional 32 seconds to perform the update. That's 32 as opposed to 26. I'm using multiple threads. I'm not sure that they are. They probably aren't. Their algorithm, when you look at the description, doesn't appear obviously parallelizable. And on a desktop at work, when you turn on 8 workers and you have a higher clock frequency, this differential dataflow code drops down to about 5 seconds for an incremental update. 10 seconds to start, 5 seconds for an incremental update. So I would actually say that differential dataflow is around the space of these numbers, depending on what you're running it on. If you're on it single-threaded on an old laptop, it's slower. If you're on it multi-threaded on a new desktop, it's faster. None of the numbers are anywhere close to the new algorithm that's presented in this paper, though. And there's a good reason for that, it turns out. Their algorithm is different. And I did something really exciting, which was to read the paper. And one of the things we'll try to get to a little bit later on today is trying to implement their new algorithm. It's not a massive conceptually different algorithm, but it's a different way of approaching the problem that I'll talk through, and you'll say, like, oh yeah, that also makes sense too, probably. And maybe it'll go faster. Maybe it won't. I have no idea, actually. Before we do that, though, I thought I'd tidy up a few bits of the code just to show you some interesting idioms that that might not actually make the computation any faster, but it'd be appropriate to talk through because they stick out at me like a sore thumb. One of them is that each time around this loop, we have this join going on where we join with labels, and joining with labels is fine. We're pulling out all these labels for these edge thingies, but by calling join map 3 times, we're taking this flat collection of labels, just a bunch of tuples, and building each time an independent index of that data. And differential dataflow allows you to not do this. It allows you to do something a little smarter, where we can say, for example, labels by edge. So we're going to essentially pre-arrange the data. We're going to take it and say, let's actually put it in the shape that that join map method wants it in. And then we'll just use it 3 times without putting it in that shape over and over again. So in this case, this is going to be labels.arrange by key, which is a method that we're going to have to go and it's in some trait that we'll have to import. Rust will yell at us and tell us what that is. But what this does is takes any data that are structured as key comma value pairs and puts them into an arrangement hash partitioned by key and grouped by key, so that anyone who wants to do data parallel work by key, including join, can just go and use them, which is great. We need to change the method that we're using. Unfortunately, Rust isn't very excited about the idea that you might call, you might have the same method with different types of arguments. So the method has to have a different name. And it turns out that's join core, because join core is the deep innards of join once we get down to where the actual implementation is. And it's a little different because it also produces an enumerator as its output rather than a single record. So we need to go and tidy this up just a little bit. That enumerator stuff is nice. It actually allows us to build some logic into the result production. So if we wanted to filter things, for example, we could. If we wanted to produce a fair batch of data from just one match, we totally could. So let's build this and let's have Rust yell at us. That seems appropriate, and it will hopefully tell us where to find some of these traits. All right. Fix this in just a moment. And arrange. Oh, is it arranged by self? Arranged by key is already in scope, maybe. Well, let's see what goes on now. Nope, something terrible. The terrible thing is the formatting. Oh, I'm sorry. That's dumb. Yeah, we need to change. We need to change this to be by edge. By edge. By edge. All right, it's good. Let's cargo build release it. Suppose we could just do the single-threaded version again. Which, if let's just make a mental note that we had 101, 151, pretty easy to remember. 71, 103, less easy to remember, but I've said it out loud now, and so it's recorded. But let's see where this goes. This will take a little bit of time to build, but it's not clear that this should necessarily go that much faster, because labels by edge is probably not the dominant pile of data here. There's a bigger pile of data, which is the stuff coming out of each of the join cores. So that essentially the left argument to join core each time is the result of joining some triangles with labels by edge. So that's almost certainly going to be bigger than labels by edge, and probably bigger than triangles. And that gets arranged as part of the first argument to the next join core. And as a consequence, that's probably where a lot of the compute and memory and just work goes, rather than in redoing those labels by edge. Though this should just be a strict win. And if we wanted to, actually, there's an even more exotic thing that we could do, which is sort of cool. Which we're not going to do this because it's pain in the ass. But labels by edge is actually exactly the output of this reduce, which is to say that the reduce goes around and is the beginning of the next iteration. But reduce actually produces its output in prearranged format. It's part of, reduce is complicated enough that when it thinks, how do I need to fix my output in response to changes to my input, it actually keeps the output around. What have I said before? Let me just write that down because it's too hard to figure it out over and over again. So its output is actually labels by edge already arranged for us. So we didn't even need to necessarily rearrange labels. We could pivot our loop just a little bit. So for example, if we essentially rotate the reduce up to the top of the iterative computation, where what we are iterating on, instead of being the labels themselves, or maybe the contributions to the labels, then we would be able to just take the output of reduce, feed it, give it a name, and then feed it right into the join core stuff, which has the potential to save a little bit more memory in principle, but again, might not be a big deal. Right. This is up and running. Yeah, cool. While it's running, just not to bore you, I will talk you through another thing that we're going to do just to be good people. Our triangle computation is bonkers. It's bad in that it produces a lot of candidates. It's a bunch of binary joins, and it produces a bunch of candidate triangles, A, B, C, that may be massively larger than the number of possible triangles we could have. For example, if a node A has a really high degree, we're going to produce the square of that degree candidates. And it's fine for the Facebook graph, because I think the max degree is about 1,000. That's not really that big. Let's check, we've got the stats here. Max degree is about 1,000, so not really that big, hooray. We also have this graph, though, this YouTube graph, which, as a graph, isn't too much bigger. It's a factor of 10 larger in terms of number of edges. But the maximum degree is 90 times larger. And when you square 90,000, I don't know, you get something big. I'm not entirely sure what it's going to be. We could, no, I don't want to figure this out. It's, billions and billions, or quite a lot. Anyhow, that's bad. It's a bad algorithm to find triangles. All right. So this took, it looks like, sort of 3 or 4 seconds less time. That's pretty, it's good that it went faster, but this isn't going to make a difference. And, I guess, a smidge less than 50 seconds to update. Because I'm curious, let's just fire this up while I keep talking. Okay, so this is a potentially very bad algorithm for computing triangles, because if it goes and produces 90,000 squared candidates first and then throws most of them away, because we saw over there, there's only, I think, 8 million edges, 9 million edges, so we can't possibly keep all of those candidates. I mean, it's just anyhow. There are better algorithms for triangle computation, and we happen to have a few of them already coded up in a different place. These are so-called worst-case optimal joins, and I'm just going to go open one up for you, and we'll copy-paste some stuff in. It's actually in the docs repo. It's not one of the sketchy, implementations. This is from work by Hung Ngo et al. And I'm just going to steal this this pile of code here. I'm not going to talk you through how it works, because although it's cool, I've talked about these sorts of things before at length. And if you want to learn about worst-case optimal joins, absolutely do. Go and learn yourself about them. Might need to fight with Rust a little bit here to make sure that I have all the right traits and such in place, but we'll see. So I think we need to steal these constraints. Put them in there. Oops. Yeah, let's put a comma. actually this whole constraint, let's see if we can get rid of this because it's kind of gross. Or it's involving, it's redundant with the lattice up above, and hash and ord are sort of weird. I'm not sure if we actually really need those. We might need to indicate what arrange by self and join core are, which I could believe. But let's see what the world looks like over here. 65 instead of 71, I think, right? And 102 instead of 103, was it? 104? So again, it looks like we might have actually lost ground in the incremental update with that change. That can't really be true. That's probably just because we were screwing around with the UI and stuff like that. It should be that that change should have been a total win. Like it just does less stuff now, uses less memory, and should be fine. All right, but that's I'm glad to have done that transformation with the label arrangement just to show you what that sort of thing looks like and some potentials for saving some memory. Let's take a peek and see if we can get Rust to tell us what it's least happy about over here and possibly where we can find these traits. Great. Here's one of them. And maybe also arrange by self. Great. And let's try it again. Wait, hold on. All right. Reduce. Okay, we need reduce also. Forgot that there are to be more methods. There are other ones. That looks like the current blocker. Oops. Oh, I just saved the file. Great. So we don't use this method yet. That's easy enough to fix. We definitely want to be using it. So let's just a quick double check here actually about what sorts of triangles it finds. God, this is hard to read. Who thought this was a good idea? Oh, for fuck's sake. So I can't, the thing I'm not clear on at the moment is whether this produces ABC triples in order without any redundancy. Okay, sorry, here we get edges are being arranged so that they go from small to large. We've already technically done that, but this implies at least that we are looking for specific orders of edges. So I'm sort of comfortable trusting that if we just go and triangle things up, on our edges, and we probably need to do something stupid here where we map them from A, B, C to B, comma, C, comma. Just to make sure that they're in the format that they're expected to be in down below. Let me just delete all of this nonsense, I think. See what happens. And try out. Check again. Yeah, looks good. I suppose we can get rid of join here apparently. I guess we don't need that. We don't need consolidate. Just get some of those filthy mustard squiggles out of the way. All right, so this is ready to go. What we're going to do with this is run not just the Facebook one, but also this this YouTube dataset, which I also happen to have on hand, and it is in some ways actually nicer. There are more vertices. Yeah, a fair bit more vertices, a few more edges, not so many more triangles, to be honest. So it's actually, and a lower average degree. So there's actually like a little bit of a less dense graph, actually. And you can see the max k over here is 33 instead of 36. I'm not sure if that tells us anything. But if we go look at the times over here for the YouTube graph, you can see like, wow, okay, it was bigger, but everyone seems to go nice and fast on these incremental updates. Great. The index creation takes 10 or 20 times longer, but which might mean a longer startup time, but the incremental update times seem fine. 2 seconds is sort of what we're aimed at, as opposed to 50, which might mean that we're going to be in deep trouble if we don't actually go very fast. But it might mean that we do better too, possibly because of the graph structural properties. Don't know. If we had lots of good time to waste, what I would have shown you actually is running the YouTube graph with the bad triangles thing, and we would sit here and look for a while, and eventually it would explode because I don't have enough free space on my SSD to hold all of the virtual memory that would be required for all of the intermediate results. Yeah, we're not going to do that. Hopefully you agree that that wasn't a good use of your time. We're now running single-threaded this Facebook wasm thing. Let's just kill this. I mean, this will go infinitesimally faster, I think, because triangles are a little faster to compute at the startup. But let's instead, let's go grab the number of lines in that YouTube thing. That dealy. And we will, let's do a two-threaded one, just because no one wants to sit around forever. And we need to not do this, but instead do this. And oh, for fuck's sake, did I? Oh, poop. All right. Let's do it faster this time. Nope, that was too fast. I was hoping to just trash one word, not all the words. Computers are still a challenge for me. So we're going to go and decrement this number here by 1 down to 6. And that gives us 10,000 output changes. Let's put 2 workers on the job and tidy things up just a little bit and go. So yeah, it took a fair bit longer to load. Okay, it's 10 times as many edges, so those numbers, the edges loaded number, and some other like round complete numbers are going to be off by a factor of 2 because we're using 2 workers, and so this is worker 0 reporting how many edges it loaded, and worker 0 reporting how many rounds did it go through, but worker 1 is doing a corresponding number of rounds of work. And to be honest, I have no idea how long it's going to take, so while this is running, maybe let's talk through the next flavor of algorithm, because once this is done, we're just going to look at the numbers and say like, oh, good job us, or total failure us, and then talk through what's up next. So it's running. Let's leave it there. The algorithm that the authors talk through, I wonder if it's easy to actually show you. The algorithm is actually sort of beastly to look at. This is it over here on the right-hand side. Blah! The one thing you might see, or one point that I can make is down here at the very bottom. Their main loop actually goes not from large values of k, of the trussedness, down to small ones, not from large to small, but from small to large, actually. So what they do, instead of trying to figure out every edge's truss value at the same time, churning on all of them, is to start small and say, let's figure out who of the edges are in level, well, everyone's in level 0, right? Everyone participates in at least 0 triangles. Who's in level 1? And having figured out a set of edges who are in level 1 by going and computing basically just all the triangles, then they go on to level 2. They say, great, let's restrict our attention to those people in level 1. It doesn't have to be, some edges might not have been in any triangles, they're gone. They were in 0, not in 1. But if we take the people who are in level 1 and say, okay, of you, who's actually in level 2? And then that involves a little bit of work, basically taking anyone who just any edge that barely made it into level 1, removing it, and updating bits of logic. Maybe there's a little bit of a cascade. Removing one edge that's only in one triangle might cause another edge to now only be in one triangle, so it's got to go also. And you unravel the edges that don't really belong in level 2. And it takes a little bit of work, but it stabilizes, and now you know who's in level 2. So you move on to level 3. You move on to level 3 by taking everyone who has only 2 triangles that they participate in level 2. You throw them away and potentially do any unraveling you need to do until you get to level 3, level 4, and you just keep going up until you've run out of edges in the graph. So this is a different approach to computing these truss quantities, and it's interesting. I mean, at every moment in time in the algorithm, we have a bit less state in our heads. Right? We don't have different edges with different labels, or we have to figure out what's the based on the weird set of labels we're getting, what are the current view of our of particular edges level. No, it just says, yeah, we're just gonna we're gonna maintain a count for every edge and the number of triangles that still exist, and because of the order in which we remove the edges from consideration, we pass through various moments where we know that we have identified the set of people at level 2, 3, 4, and so on. So I thought we might try to write that algorithm down. It's interesting. Or thinking through how it would look in differential is interesting. I think it involves nested iteration, which is cool. My laptop is making some jet engine sound, so I'm sort of curious to check out the activity monitor and see if we are well over what we're allowed in terms of memory here. It is very possible that this doesn't actually run cleanly on my laptop. It's just a little bit too big, maybe. In which case, I'm happy to admit defeat from a laptop point of view. This is a thing, unfortunately, this is a thing that would have been cleaned up by the dogs stuff. It reduces the memory footprint quite a lot, but is incorrect at the moment. So this isn't good. I will happily run this on my desktop at work to try to get some numbers there. I don't think the authors here reported, well, maybe if I knew more about their algorithm, I would know whether it has a nice bounded memory footprint, in which case, I think it does actually, I think they worry about that actually, about the auxiliary storage. I think space here might be in addition to the graph. So they're probably pretty lean actually, and they could justifiably say, like, what a mess, your system is so fat and sassy. Yeah, probably right. So, cool. I'll edit this up, I suppose, and post with some numbers about how this looks on a work desktop, or possibly, if it's a total disaster, I will not report that, and instead record some more video explaining what the hell went wrong, and or investigating what went wrong, and hoping we can find it. But what I'd like to do now is save this binary. So let's vector source bin cp main rs to source bin. Let's call it optimistic rs. What? Where am I? Oh, sorry. Right, good. Doobie. Great. Now, in principle, we could do, I think, cargo check. No. Okay, cool. So this is now just not the main program we're working on anymore, but we've saved it so that if we stash this in the repo, we can remember where we got to. All right. Let me talk through what I was thinking for this modified algorithm. We may still want to keep triangle computation around. In fact, it may be crucial to keep it around. We will see. So my intended plan was actually, yeah, we're definitely going to keep triangle computation around. We don't want to redo that over and over again, and it's pretty cheap to do once at the beginning of time. And what I think we're going to do is tidy up some stuff first. So we'll probably have to add these back in just a moment. So I'm going to write some comments because I like writing comments as a way of me convincing myself I understand what's going on. New algorithm starts from a set of triangles and a candidate leveling of each edge. We're gonna get there. Now this did I screw you autocomplete? This candidate leveling is going to initially be 0. Basically, we're going to start with initially 0. So we're going to start with the belief that every edge, we did use at level 0. We don't know any better than that, and we're going to progressively increment this, basically. Progressively incremented each round, and edge survives, essentially. Survives means still has as many triangles as its level. So we're going to essentially iterate incrementing levels for people who continue to pass the tests, and ceasing to increment the levels for people who fail to pass various tests. The end result of the iteration being the labeling for all of the edges. So let's figure out how to write this thing. We don't start from these edges. We actually start from an empty collection, because the way I'm going to do this, I should probably write notes about this just to make it sure it doesn't sound insane, but we're not actually going to maintain a collection. This is not actually a collection of edge, level. It's actually just going to be a collection, I hope this works out, a collection of edges where the multiplicity actually is what tells us what level the edge is at. So each round an edge survives, we'll add one more copy of that edge to our collection. Cool. You might say that's a bit weird, and you're probably right, and we'll see how it goes. It seemed like it actually made sense when I thought through what I wanted to do with that information. So what I think we want to do when we have edge, level, is effectively to subtract out level points from the triangle accumulation stuff. So if we go and we ask, hey everybody, do you have enough triangles incident on you? And then we subtract from everyone their level. I believe this does the thing that we want to do, which is to say you need to have evidence in addition to, to survive onto the next level, you need to be greater than this number. And that's one way to express that is to subtract that number from it and see, do we actually have a strictly positive record remaining? And if not, great, we're going to stop talking about you. But everyone who does have a strictly positive record remaining comes to our attention and survives on to the next, to be incremented in the next round. So let's do that. Let's start. It doesn't really matter, I think, what we start from. We've got a bunch of edges. We are going to just filter them away, just delete them. Right. So that's pretty easy. Sorry, it's easy once I figure out how to shift down, not control down. Great. I'm going to get better at this, and all of you are going to be very impressed. And but that will be in the future, not right now. I swear I will uninstall this Rust plugin, which is just a disaster for readability. So we're going to throw away. This is seriously upsetting. We're going to take a moment to figure out how to turn off this Rust plugin. I forget the exact key combination to bring up the equivalent of package manager for command palette, maybe, yeah. Extensions. Just show me the extensions and let me disable specific, disable Rust extension, basically. Show running extensions. Oh, what was this? It's not what I wanted. Is there a nope, don't want this. Extensions. And if we pretend we want to install some, great. Now I can go and blow the crap out of the Rust one. Yes. Off you go. You are terrible. Let's see. So we need a reload. All right, do the reload. Quit and restart, maybe. Great, and now we have no horrible squiggly lines that we have to look at, which makes me at least a lot happier, and the Rust plugin can figure that out on their own time. So what we have now is we're iterating. We don't have labels each go around, I guess. We could call it labels. Let's call it levels instead, just because I kind of like that. And what this tells us is, the intent at least, is levels indicates the level of an edge by its multiplicity. So everyone is initially at level 0. That's cool. What do we want to do with this? Well, we want to, it's a good question actually. What do we want to do with this? My sense is that what we want to do, sort of puzzle this out live on camera. My sense is that what we want to do to make this happen is to subtract down the multiplicities, these levels, sorry, to take the number of triangles everyone participates in. I'm going to say this out loud, and it might turn out to be false, and hopefully by saying it out loud we'll find that out. Take the number of triangles each edge participates in, subtract from each edge its level, and then run a sub-iterative computation that continues to unravel that. That basically verifies that you actually are participating in any triangles at all, and deleting people who participate in no triangles. So people who are in level 1, for example, who participated in one triangle of interest, will have their score decremented by 1, and hopefully what will happen is that we'll essentially see that reproduce itself in this verification step, where it will unpeel all of the edges that had their level decremented by their number of triangles they participated in decremented by 1. So we're essentially doing a Boolean, do you actually participate in triangles test once we have subtracted out this count from people. So, having said that, I'm not entirely sure I believe this, but let's see where it goes. This is the intent is to find something analogous to the algorithm that was implemented in the paper, and this is, I think, the closest analogy that I've come up with. But let's see where we get. So we have we're going to need to bring triangles into the scope for sure. No. That's not the correct way to spell triangles. So we bring triangles into our scope. Let's remove the stupid. I mean, maybe we'll want that again, but that's just confusing and it's probably going to screw us up somewhere. So we bring the triangles in. I believe we basically want to get some initial scores now for everyone. So we're going to sort of steal this flat map logic here. If your hands are off by one key on this, you get aligned to all these other crazy control keys that open up Spotlight and stuff like that. So we're going to let the initial score be equal to this mess applied to triangles. Great. We will want to subtract now, I believe, subtract levels from this, which is concatenation with levels.negate. And let's leave it like that. Let's trash all this. We might have to find that again and add it back in, but for the moment, I'm just going to ignore it. So, all right, here we are. We have said, well, looks like everyone participates in a bunch of triangles, but we've introduced now with this negation some barrier that says, yeah, actually, unfortunately, some of you are going to need to get over certain humps. And what I think we actually want to do now, this could be a little bit wonky, so let's throw in the threshold thingy, which I think we'll have to look up the arguments because I've forgotten them, but I believe threshold, it means to take an accumulation, like a count, and some logic saying, you know, whatever you want to do here. So if count greater than 0, then maybe we produce a 1, else 0. So this does an important thing that I think will be important, which is takes negative numbers to 0. And that's important because I'm not 100% confident that as we start to delete more and more things here, that well, this has to be fine actually. Maybe this is okay, but in any case, we want to hit things with a distinct to get down this sort of Boolean edge present or absent thing. And our plan now is to essentially try to unravel, I think basically to try to find the one truss, which is to tell this fairly boring graph, just a bunch of edges, no levels or anything like that, to unravel itself to find those people who still participate in a valid triangle. So we've intentionally tried to effectively delete people at their level. Like once we've actually identified, okay, so here's a claim that we might be able to verify or falsify. That once we've actually found the level for an edge, that concatenating in this negation here causes that edge to effectively to no longer participate in any triangles at this point. So this is a collection, right, of edges. What have I screwed up? Sorry, we don't actually want. There's no label there. Sorry, just minor edits as I. So a claim can be that by correctly subtracting everyone's label up through k or whatever iteration that we're on, we have left a graph that if we actually just try to find triangles in it, we will only find the k+1 truss. It's an interesting thing to conjecture. I feel like I'm just making that up at the moment, but I'm going to write the algorithm assuming that's true, and we will see what happens. I'd be delighted if it's true. My intuition tells me that this is either right or close to right, but I'm having a hard time articulating it at the moment. So what we need to do now is describe a new iterative computation that will maintain a set of edges. We've got a set of edges, but only keep them around if only maintain edges if they participate in at least one triangle. And how are we going to do that? So we have our set of static triangles, and what we'll probably do is probably take our set of static triangles, do a semi-join with the set of edges, sort of like we did before. We did joins before, but do a bunch of semi-joins with the static set of triangles, and that will only pass triangles through that still have all of their edges present, and then we will hand out some scores, sort of like we did up here, to each of the present triangles, present edges, to each of the edges still present in a triangle, and then you continue on to the, you stick around if you're participating in at least one triangle. That's a bit of a mouthful, but let's try typing it and see what happens. If nothing else, this is like a weird and interesting algorithm that does a thing, possibly not a good, possibly the thing it does is not terminate, but that's good to see what those look like as well. Now we have, let's call it like active. These are edges that are still participating in at least one triangle. Now we're going to need to bring triangle into scope again. So let's actually steal this. Oops, I was wrong. And we're going to repeatedly semi-join triangles with the active sets, which looks like what? That looks like we have to put it in the right shape first. So triangles dot map B, C to, let's do A comma B first, comma C. Oops. Dot semi-join. This is going to be another example where we're going to semi-join by exactly the same thing over and over again, and we could benefit by pre-arranging it once. Same sort of thing here. A comma B, comma C goes to something different. Doesn't really matter what we do next. Let's do A comma C, comma B. Semi-join with active again, and one last what do we have? We left it as A comma C, comma B into B comma C, comma A. So this should now be triples B comma C comma A, for which all of the edges are present. We then want to essentially reward anyone who's still around by 1 point, and just make this look correct. Great. And at the end, I think we just want to, I just want to do it distinct. So what this is saying, we can even just make this horrible, actually. Horrible in the good way. We can totally just tidy this up like so, and just make one long, massive, utterly unreadable thing. So, let me just spell distinct correctly. So the idea here is that from our initial set of edges, which are a subset of our original edges, those that are currently sticking out above their proposed level in terms of the number of triangles they participate in. We take those edges and we feed them into our iterative computation, where we say, all right, edges, let's confirm that you all are still part of a bunch of triangles. And having said that, that sounds really stupid because, sorry, in what way is this fucked up? Yeah, I'm not even sure we need an iterative thing at this point, do we? Because, sorry, if you participate in a triangle, then you participate in a triangle, and there's no reason to iterate through anything. So what are we? Let's see. What are we trying to iteratively unpick here? If I wish I had a pen to draw on the screen to sort of talk you through some of these examples. So we have a bunch of very tenuous triangles, let's say, and I'm thinking, think about drawing up in your brain, since I can't show you, a path of triangles. Can I draw? I can wiggle the cursor around a little bit. So imagine a path of triangles. Maybe I can draw it in the comments. Maybe not. Certainly not with that key. So we've got a path of triangles we might draw that involve A, B, and C. This isn't a great triangle. This is an even worse triangle. Okay, this is a better triangle. A, B, C. Then possibly D and E. Oh. So B, C, D is thinking, the edges like B, C, and B, D are thinking, hey, I participate in 2 triangles, I am hot shit. And actually, we need to add one more to this to make the example compelling. Cool. So I'm thinking triangles basically between all of the little triangular regions here, ABC, BCD, BDE, and CDF. The edges BC, CD, and BD are all thinking like, yeah, cool, I'm in at least 2 triangles, right? Because hot shit. And they shouldn't be, right? They should end up in level 1 because the triangle, or the edge AC and the edge AB will vanish. Actually, they're only party to 1 triangle, so they'll only be part of level 1. BE, BD is only part of level. So these triangles that stick out from the side are only there at level 1. Which means if BCD got to thinking I should be at level 2, we would quickly find out, no, you're definitely not. Now, how do we want to discover that? We come into this with a 1 on all of these edges because they all participate in at least 1 triangle. They're all level 1. In effect, we want to decrement the excitement about AB and AC, BD, BE, CD, CF. So we do this logic just above and say, like, okay, how many triangles are you part of? Let's subtract 1 from that. They go away, essentially. And we're still left with a triangle, BCD. Because each of those folks had a count of 2, and it's they need to keep going. So I wonder if what we actually want to be doing is iteratively updating sort of this bit of logic up here, where instead of giving everyone points for everything, we are continually rescoring them based on the current number of surviving triangles. And I feel like it's bad to compare that against the cumulative level threshold, but maybe that's actually right. Yeah, that's probably actually right. So how do we write that? How do we say we have a bunch of triangles coming in? We are going to iteratively change some scores. We're going to score people and say you've got the following current score, which is sort of what we're doing right here. And then we'll be a little negative about it and say like, yeah, but actually you're not all that. And then pass people through if they still survive this. Send them back around and say, let's try this again without those edges that are currently scrapped, basically because they didn't stick out above their level. And then we update that computation effectively and say, tell me again about what level you think you're part of. And that's the moment, for example, which BCD would say like, oh, I give up, you're right. I do not stick out above my level, so I should not go on to the next round. So I'm tempted to try to figure out how to write that iterative computation, which iterates over active sets of edges, I believe. So it's just the set of edges that is changing, and those edges are those that stand out above their threshold. So actually, maybe what we can end up doing is sort of stitching that in down here, actually. So it might be that some of this logic wants to migrate down to here, so that perhaps instead of distinct down here, what we really need to do is to compare this against your hypothesized level, and then put a threshold in instead. Fascinating. Let's try that. This is a really bad way to program, by the way. Like, if you read that paper that I linked, they have like theorems and stuff. Clearly like they've thought ahead of time about how to do a thing. This format is a little bit weird for like trying to come up with. What have I done? Trying to come up with correct graph algorithms. Just watching someone make them up in front of you is a weird way to go about it. We need to bring in level, though, also, because level is something that's external to this to the scope. Level equal level enter. Right. So level is this, this bunch of multiplicities for people based on what their hypothesized level is, and we will take our active set. We're going to restrict all of our triangles down to just the active set, and then ask, having awarded points based on this active set, who among you still juts out above this threshold? And I wonder, we might have an off by one error here, and that we might actually want to essentially define people who are, being at that count is fine. So I guess, sorry, no, this is fine. So if we come in with level 1, and we say who actually juts out above 1, these are the people who for sure will survive at 2, I think. And so it's totally fine to advance them to 2, having seen positive evidence that they survived past 1. So, so let's give a name to these folks here. To advance. So these are going to be people who should advance to the next round. And I think what we want to do here, we probably want to delete this nonsense, like that means nothing to us. And what we probably want to do here is set. So we need to describe what is our next iterate here. And I think we just want to set this to be levels concatenated. So levels.concat to advance. So let's talk this through. We're going to start out with a whole bunch of nothing, right? This empty collection that comes in. We're going to initial. What was initial? Oh, sorry, we do need to grab some initial set of edges. Let's bring those in as well. We commented out, our edge set. We could in principle get this from our triangles, but we're not going to do that. So edges dot. So cool. This starts us with a full set of edges, which is great. We want to start with a full set of edges. And then we are going to ask, okay, let's assume all of you are active and all of you are at some level. This was initially 0. Let's see how many of you participate in triangles still. And this is going to be kind of boring one that just says all of you are active. All of the triangles out there, yeah, you're still triangles, good for you. And what does that mean in terms of who actually gets points? We'll subtract a whole bunch of nothing. Essentially, what we're doing now is we're moving from the full set of edges to edges that participate in at least one triangle, which is great. I believe we'll iterate and come back and just converge at that point and say, huh, oh, okay, that was easy. So the 0th round will then produce, to advance, a set which is everyone who should be in level 1, everyone who participates in at least one triangle. Cool. If we go around now, back up to levels up here, this now, let's imagine, second iteration, this has everyone who participates in at least one triangle, but none of the edges that don't participate in any triangles. We will head on in down here and say, cool, well, with that in mind, let's start again. Start over, in your brain, start from scratch is what the code says. We're not going to actually, the system won't do that. Start from the full set of edges. We will, again, start to iterate through and say, full set of edges, what do you folks think about triangles that exist? We're still going to get all these triangles down here. Awesome, 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 awesome. And then we're going to say, haha, but some of you, just having a single triangle is not good enough. We're going to subtract 1 from basically everyone that participates in a triangle. So the only people who got points, of course, were people who participate in triangles. We're going to subtract 1 from everyone who participates in a triangle, and then say how many of you still have some points left. And the answer might be for some people, yeah, I was part of two triangles or more. That's great. You'll stick around. And people who were part of, unfortunately, only one triangle vanish. Now, this means that we might have more work to do. We're going to iterate around. I need to remove this semicolon. We're going to iterate around and say some of you edges didn't survive. That's problematic because it means that we're not at a fixed point yet. So we need to take a slightly reduced set of active edges, update this logic here, and do it again. And those edges that went away no longer contribute to triangles. And potentially some of your scores might have gone down, and potentially some of you might now fall below threshold and yourself vanish. But we'll converge. Once that has been sufficiently unpicked, we will converge, and to advance will contain, I hope, those edges that participate. It should be advanced to the second level, and we'll advance them. And keep advancing, and we'll eventually get something out here that we should probably count, I think. So this is going to be a bunch of edges and multiplicities, but we need to produce edges and counts. So if we just do count, and we probably have to do a map to change the type, because the count would be an I size. So it's going to be an edge, so it's going to be a pair of an edge and a count. And we want to make it just be a pair of an edge and a count as node, just to make the types work out. Oof. Well, I'm ready to see what happens here. I'm very curious. Okay, we have to manually type cargo run because to get rid of those red squiggles we had to, but it's really not so bad. Sweet. All right, what's wrong here? 146 has some semicolons missing. Oh no, we need curly braces because we don't just have one statement. That's fair. We get curly brace down here. And we need to add this trait count so that we can count things. Save it. Level, okay, this should have been levels apparently. Levels dot scope, yeah, good. 147 here. That could be levels, levels, and levels. No method named semi-join. Okay, we gotta get the join method going. Mismatched types. All right, we return something with a. Okay, we need to. If we have an iterative computation, you actually need to return the thing. You need to not end with a semicolon because that doesn't return it. Let's get a new readout on. Oops. Focus over here. With the threshold. Add the threshold. Somehow this doesn't feel like this is the right workflow, but this is what it is. Well, oh, right, okay, closure expected to take 2 arguments. We got to figure out what threshold actually does. I think you're actually allowed to look at the data as well, or sorry, forced to look at the data. But let's check. So threshold function from the key and the accumulation. Great. So we don't really care what the key is. We don't have a different threshold for different edges. Is the main point. So we can write this as edge, comma. No, I guess. Oh geez, now I gotta. Takes 2 arguments on a pair, sorry about that. Expected a reference to an I size, but found an integer. Cool. All right. Well, it builds. Let's build it up in release mode and get ready to stand back and watch everything catch on fire and wonder tremendously if it produces even the correct answer. And if we could, in principle, test to see if it produces at least the same answer as the other implementation. That's going to involve some more copying and pasting of bits of code around, but let's get a read on whether this actually runs, and when it runs, if it takes forever, if it takes lots of memory, if it just terminates immediately and produces the wrong answer. Lots of fun things could happen. But I think this is now more in the spirit of their algorithm, which is a nice property, I think. One that iterates primarily through levels, so up through levels, building up sets of edges in each level, and within each level, it needs to do some iterative computation to unravel who actually lives in that level. Their algorithm that they've done is sequential and literally just goes, has a priority queue, and I think probably, and just keeps going through edges. There isn't this complicated doubly nested fixed point capo. They're not actually writing a computation that needs to describe its behavior in a repeated pattern over and over again, like we do. And that's clearly a bit of a pain for us, though it leaves us in a nice spot where we automatically get incremental updates for changes and things like that, which their algorithm is essentially a hand-rolled incremental updating algorithm for this one specific problem, using some clever advanced reasoning about structural properties of the problem. Yeah. That being said, since they've done the work, you might as well use their algorithm. But if you want to change anything, or if you wanted to scale out to multiple workers, or if you wanted to handle not just one batch of 10,000 updates, but 10,000 individual updates, plausibly this implementation that we've done, either of them, would give you something that their algorithm didn't give you. And really the story, I think, is meant to be that, I'm just talking while it builds, by the way, if it saves you time to do things this way, right? So if you're a graph theory expert and like to spend your time coming up with new algorithms for updating structural properties of graphs, great. I don't think you should stop. You should keep doing that. If you're not such a person and you have a graph problem that you need to figure out, and you'd rather not spend 6 months or more doing the legwork to try to get some theory in place and stuff, we wrote the previous algorithm in like an hour or 2 hours, and then wrote a bad version. And this one, I have no idea how long this has taken, but not an epically long amount of time. It's not done yet either. First of all, it's going to take another half hour to compile, but it might not yet be correct. All right, half hour. Sorry, it's only 3 minutes to compile. So let's try cargo running this on. Let's just do the small graph to start, because we don't know how things are going to work. So that lives over in and I don't remember. Let's start with something small, because if this blows up, we don't actually want to force ourselves to watch. Let's do something even. Let's do the smallest. That's not right. We don't really want to watch it catch on fire, showing us no output. So this will let us see some things as we go. Oops. Sorry. Right. We have to specify which one, because we have multiple binaries now. So let's do that. And I think this one just inherits the name of the project, which I think is graphs or something, like super not interesting. All right. Now, in any other world, this would have started pretty lots of exciting output. We're definitely not doing that, so something's probably wrong. All right, super small memory footprint, super high CPU utilization, probably wedged is my guess. So, what's the right way to think about this? Actually, well, let's do a few things while we're talking. Just oh, it's already built. Nice. Surprising. So if we run this with the optimistic code, the one that is believed to work better, at least. That's what we wanted to see coming out at us. And didn't see that. So, but we can totally expect, actually, let's do a debug version of this. That's just going to take a bit of time to rebuild, but I want to get a handle on, if we're going to start working on this thing, we don't want to be doing release builds each time. So, and one thing we could totally start to think about doing here is this levels thing is something we can watch. So we can so levels.map. If we take everyone and say we don't care who you are. Where are we? We don't care who you are. We just want to see the changes at each round. Okay, what this is telling me, looking at it, is okay. If we can eat 5 seconds of startup time, then we can save potentially a bunch of time, compile time. I think we're going to want to do that probably. Consolidate, inspect. Oh, sorry. X. All these muscle memory things that I used to have on lock for all of these weird format strings that I'm needing to relearn. Sweet. So we can totally print out, just format this a bit more nicely. In each round of derivation, what are we seeing in terms of levels? We're seeing nothing, we're seeing lots of stuff. Might help us unpick why are things taking so damn long? Like why are we not converging, and why not? Just to double check, coming out here, to advance. So just like good things to do is mental check to like, do we expect these things to converge or not? We expect levels to grow, not to shrink. So we always have at least levels, and we add in add into advance, which I'm hoping, based on what comes out of threshold down here, is something that either has a 1 or a 0. So this should just increase by 1s and 0s. If it ever doesn't change at all, of course we've hit the fixed point. Good for us. And inside here, do we expect active to always shrink, essentially, is what we're kind of looking for. Cat, threshold, well, unclear. Let's get it spinning at least on this. While we talk out some of these things, we can at least start to see, for example, how many folks do we have at each level in the. We haven't even made it past the first batch, right? So, how many folks do we have in each level of the first batch? And we can make the batches even smaller, though. Sometimes what happens, I wonder if this is happening here. Sometimes what happens is it just takes a little while to get going because there's, though I think that's not true here. So even in the very first few rounds, we're seeing stuff happen. We're seeing actual triangles, or we were over there. What are we looking at here, actually? Oh, I see. This is in the first batch of whatever 1,000 things. 74 people were in level 1, 27 were in level 2, 52 were in level 7. All right. So we still seeing nothing, which implies to me, at least, that first time through here, there's nothing. That makes sense. So we're not seeing anything. Probably means that we're just spinning indefinitely in here for some crazy reason. Let's try to crack that open and see if we can at least track what's going on here. So let's take active, which is a set of edges, and let's just see how many things there are in it. Basically, just going to steal this code. I'm sorry, what? Why do I not have access to consolidate inside here, but I do have access to consolidate outside there? Had we not, oh dear, had we not saved this file potentially? And that's why because it's complaining. Okay, yeah, I suspect we did not in fact save the file, and the lack of printing was in part because the compiled code didn't actually have the print statement in it, which is embarrassing. But now we have both of these prints in here, and we can see both of them, though that hypothesis that we were stuck at round 0 is not necessarily the case anymore. Well, I'm going to blow away these things just so that we've got a little bit more space to look. Should not have edited that file. Okay, I haven't saved it though. If you do clean up in your file while code is building, that just means that you're going to have to rebuild it again next time, which is kind of annoying. Alright, loading up some data. 5 seconds, I hope. Alright, we're seeing a bunch of stuff, and then we just vanish. Why do we just vanish? So we have effectively, well, actually, sorry, I'm not entirely sure where control is at the moment. But okay, so this is good. Good. I don't know, but we're stuck here. Oh, okay. So we have to be a little careful because one thing that can be happening, we've forced everyone into basically to a value we don't care about, and then added them up and said, "Show me what's going on." If it turns out that the thing is changing, so maybe so like hypothetically, we're removing one node and adding another node. Hopefully we're not doing that, but if we add one node, remove another node, this consolidates down to 0, we don't see anything. And if we're stuck in an infinite loop, adding and subtracting things over here, then got a little bit of a problem. So one way we can look at that instead is to not look at this, but if we instead do usually do this, so hopefully this works, do a count. So we're going to say, are you positive or negative? Who knows? We don't really care what your value is. We do care about the count, though. And let's look at your count. So this will show us how many folks have changed by various quantities. And I'm going to steal this for just up above, too, in case that's the place that we have screwed things up. Which button did I press? Oh. So let's take this, and what we're really hoping to see is a spray of horrible printouts from wherever we happen to be stuck. That hopefully will give us some clues about some stupid piece of logic that causes us to something dumb like if levels is negative for some stupid reason, then this would actually introduce data and cause a person to exist. Yeah. There's a very legit question of like, is debugging a program like this the right way to try to get your head around what's going on in computation, or like how, in principle, there's some nice properties here, like this iterative subcomputation, is meant to do a thing, sort of meant to have a spec. We could factor it out and try to test it independently, and it should. Ooh, okay, what's going on? No, it just goes off into space and does nothing, or not nothing, but like. I mean, it really does feel like we are not. I think we've caused some massive problem somewhere. Like we have some operator we've tricked and we've fed some negative number in, and it's counting down from -1 until it becomes positive or something comically crap. Um, fascinating. Or too bad. Or, let's see. I wonder. Well, there's a bunch more printfs we can put in to try to figure out how far we actually got. And in the worst case, what we do is we fire up instruments, which is the Mac profiler, and have it tell us where the code's currently sitting. Ideally, oops, not. I mean, this is small, so we can totally eat a big spray of data if we make it this far. That's fine. So let's try this. So if we don't ever see this, there's definitely something interesting, which means that we're stuck in some loop somewhere. We could also turn on timely logging, which will tell us what's being scheduled, what's not being scheduled. Or sorry, it won't tell us what's not being scheduled, but which operators are scheduling, which will tell us whether we're in a tight loop, failing to do anything, or we are stuck in an operator that's running forever for some reason. This is a little surprising, though. I'm not used to seeing. I mean, I haven't written doubly nested loops in a little while, but I'm not used to seeing this getting stuck. I kind of feel like this sequence of videos might be Frank writes some code, gets stuck, and then calls it and goes and does something else for a bit, and then comes back and realizes what stupid thing he did. Yeah, no, we're not breaking out of the loop properly. So we have tests that test doubly nested iteration, like the strongly connected component stuff definitely tests these sorts of things. The last stuff we saw was active, and active in the 7th iteration. No, I'm trying to get a handle on the first moment at which things have gone wrong. So we did a few rounds there, and then we got stuck. But these were boring rounds. Apparently, these were rounds where actives immediately just bailed out and said, "No, I'm done. I give up." Just to check that we're at probably 100 CPU, 100% CPU. We are for sure running. Not really using any memory. Running in place, doing nothing. No, we're not doing nothing. Doing something. What the hell are we doing? All right, let's turn on instruments, because if we're doing something, it would be great to be able to see what's going on. So instruments is here, and yeah, come on. So a different target. This is a lot of clicking I gotta do. Sorry. Projects. We're in debug at the moment, doing graphs. We need to give it some arguments, so let's do It's not entirely clear if I recommend this tool, but it's the only thing I know of that will tell me in a running binary what's actually going on at any given moment. So we think for several seconds at least, we're going to be parsing some data. But at some point, we're going to stop doing that, and we are instead going to end up doing whatever differential is doing. I mean, something's going on, but it's not. We're moving. There's no one villain who's at 99% CPU. So let's shift over to looking at things by weight, which allows us to sort of dive down and say, all right, the worker is stepping. That makes sense. Step, 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 step. Hooray! And when we ask, what are you doing while you are stepping? It's going into some step graphs. It's scheduling folks. When we schedule folks, there's one of the operators wants to run. When it runs, it's got a closure. In that closure, again, this is horrible. I have no idea what any of these methods are. So there's some operator that's happily grinding through all of its inputs. So it looks like data is actually circulating. Ooh, okay. Okay. Hold on. I think I know what's going on here. Do I know what's going on? Yes. All right. Okay. This is well, if I'm right, it's not a bug, but it's a stupid. If this is bad of differential data flow. So differential data flow wants to be fast. When you define, as we do here, what the next iteration will be, differential data flow happily puts these two things together. It says level is concatenated with to advance. The way concat works, it says, yeah, anything comes in on my input, I'll just send it out to my output. I'm not even going to look at it. I'm not even going to think. And one consequence of that is that levels feeds directly back into itself. Mathematically, it's fine. We're concatenating with two advance. This is all good. But basically, what was supposed to happen is we were supposed to pause for a moment and say, like, hold on, before we circulate this around again, shouldn't we at least reflect and see if there's anything to do, as opposed to, for example, a positive one here and a negative one here. Positive one here and a negative one here. We're just going to circulate those things around forever. We're never going to think like, maybe that's not such a great idea. So that's I don't know. We don't necessarily want to have to put in a consolidate for you. This might not be it. Oh no, I haven't saved the file yet. Thank goodness. I'm very upset. Okay, yeah, right. So we don't necessarily want to have to put in a consolidate for you because many operators are already consolidated. And really what we should probably do is have a bit of metadata attached to each collection which says, is this stream consolidated or not? And if it is, great, don't need to do anything. If it isn't, either we need to put in a consolidator, we need to warn you, or something, because as you saw, figuring out what the bug there was, assuming that's the bug, but that was definitely a bug. Discovering that bug is annoying and confusing even to people like me who are supposed to understand how this thing works. So plausibly, we should actually maybe put in a consolidate everywhere and maybe have a less safe version that allows you to go fast if you want to go fast. All right, we're off and running now. Let's do a release build. Debug is going to be quite slow. build this up. This took 3 minutes last time. Maybe it'll take less now because of incremental stuff. But okay, so that was really, though, it appeared to be the main only. I don't know. The problem that was keeping us from executing, at least. We haven't even seen if we got the right answer yet. But yeah, right. That's definitely on me to figure out how to make that more, I was going to say idiot-proof, acknowledging that I was the idiot who both did it badly and succumbed to it. So, yeah. But well, now actually, shit. We're gonna see a lot of output now. Maybe that's fine because we're gonna do a really pretty big batch. No, we don't want to see this stuff down there. That's gonna be enormous. Sorry. I don't really want to see this. Might be interesting to see this stuff. You know, with one massive. No, we don't want to see this. We want to see. Since we're less mystified, we can dial back the. What are we willing to tolerate as output? Sorry. It's 10 in the morning, which means we started earlier than that, which is just when I woke up. At work, what I'm doing right now is screwing around with various intermediate representations that make compiling these things a fair bit easier by realizing that basically we're doing the exact same thing over and over again. It's sort of dumb to write custom code for each of these semi-join operators and map operators and stuff like that. And that with the appropriate bit of IR, we can have precompiled a whole bunch of these things so that when you want to run your program, we just pick from the little menu of precompiled bits of operator and stitch them together in a few milliseconds, and all of this downtime is removed, which, what a fascinating idea. Yeah. We're off. All right. Let's make the batch size a little bit bigger so we don't have to look at all this crud. What was our batch size? We actually have that. Keep going back. No. Okay. We gotta go word count this thing again. It's too bad. Right. 807037 space tidy. We get to watch the computation unfold. Oh. Slowly, possibly. So this is us discovering each of the levels of the computation, the truss structure. No idea if this looks like good performance or bad performance. The competition before was 100 seconds. Who knows? My theory was, maybe this is wrong, my theory was that this would accelerate as the cores got smaller because we are in subsequent rounds of the outer iteration, as we add more things to levels, so as we change levels, we're definitely changing a little bit this computation, but as the changes to levels get smaller and smaller, they are, you might think, potentially less and less impactful. That might be false. But the theory being that like if levels, if at some point we're just adding a few hundred people to a new level, then tracing through what are the consequences of a few bit more negative numbers in here, the exact same thing happens when we're in level 18 now. We're in level 18. The exact same thing has happened to everyone in level 17 as happened to them in the times before. Maybe with a little bit of modification that they don't get the level 18 points that they used to, but this looks like it's okay. It looks like it's speeding up in the sense that it's moving through the iterations a lot faster, but it's doing a lot more of them. There's sort of a deeper bit of unraveling that needs to happen. Now look at it go. Zoom! I think we're not expecting to go past 34 if we're doing things correctly. Oh, jeez. Oh, yeah, cool. Now that definitely took longer. 161 seconds instead of 100. And now we're doing our incremental update. So one fundamental difference, I suppose, between the way this algorithm is written, and I wonder, we might be able to figure this out, we might not, but one fundamental difference is that as we move from level, let's say, like 1 to 2 to 3 to 4, we are actually doing work proportional to the size of the trusses, basically at that level. So if there are, a million nodes at that level, we go and we subtract, or, we increment, each of them by one more, and then subtract by one more, and each of these computations. So we're doing a bunch of work that I would say in this SIGMOD paper they're just not doing, right? Because as they move from level 1 to level 2 to level 3 to level 4, they're only playing around with the people who have dropped down into the what's the way to say this? Right, have dropped below the threshold. So whereas they are increasing the threshold by 1, the k by 1 with each iteration, we're doing a different thing, which is decrementing the presence of every edge by 1 each round. And that's a fairly major change. It's not super complicated, but it is a big change. There's like lots of data that gets shuffled around and does that. And I'm not sure if there's a good way to avoid that, because if we want to write an iterative computation, we need to have it do the same thing each iteration. We can't change the program logic iteration by iteration. Particularly, we can't change the threshold really iteration by iteration. Or if we do change the threshold, we have to go and do some new tests. Like if we change the threshold from k to k plus 1, we have to go and test everyone out there, not relying on the fact that a priority queue shows us things in order, and as soon as we see a k plus 1, there's no more k's after it. So that's an interesting thing to think about. Like, is there a way to structure computation so that we defer work until such a time as it is worth showing up and doing a bit of additional thinking? Can we skip over all of those people who have 57 triangles attached to them until round 57? And in principle, this is still running, by the way. I assume you all can see that. There's no way that this is going to improve on the time, at least not yet. Not without some more advanced thinkings, which I think I'll probably do offline. But there's some cute things that they've shown up in the blog post before, where we have used the timestamps to schedule work, essentially, where we can take data and migrate it into the timestamp. We can programmatically delay updates based on the data in them. And we could in principle do that here too. We could say, everyone, you are, let us know how many triangles you participate in. Great, we're going to delay you until that round. So great. We don't need to have a conversation with you every single round until we get to that point. Or possibly, if your triangle count gets decremented before then, we might need to change the round in which you were delayed to from 57 or whatever down to 46 or whatever new number of triangles you happen to have been downgraded to. And this has the nice property, I suppose, that the work gets deferred until then, right? Like we don't even have a conversation with all of these crummy folks. This is taking forever, isn't it? Holy crap. Well, we're gonna let it run, and at the end of it, I think we're then going to take a little bit of a rest, and the smugness levels have downgraded for sure, but I'm a little pleased actually that it seems to at least compute the same answer as before, 34, and as the largest truss level. But clearly we have not identified a faster way to go about doing this. We have not in any way reproduced something that efficiently peels off the truss layers. But it still seems like an interesting thing to try to think about and make happen. We have the exact same problem that we had before also, by the way, where like all of these semi-joins are just really, this is silly. I mean, they shouldn't be, there's no particular need to have quite all of this state stored here. Like we're doing these lookups that could be stateless in principle if the dog stuff were correct. We're fixed. We're now very far away from comfort zone with it, though. We're now in three-dimensional timestamp land, where we have an outer timestamp that's changing the input, a round of iteration for our k, essentially, and a round of iteration as we unravel the graph to confirm who's actually still in the k, or who should be advanced to the k+1 round. So this is very much not a dog stuff works in for totally ordered timestamps, and these are absolutely not those. But the main art with a lot of differential data flow programs is trying to figure out how to write your computation so that things change as little as possible. So that if we could write these iterative computations so that when there were small changes to levels, relatively small changes happened here. For example, this is possibly silly, though maybe clever. We could imagine delaying levels. So what we're sort of doing, which is possibly bad, is as levels is changing, we're actually interfering with the derivation of, so as we go from k to k+1 or something, we're actually interfering with the derivations of the levels 2, 3, and 4 counts. Because they got some triangles probably from these these higher level people, and those are now falling out of the computation earlier, which is kind of silly. Like, we don't really care about that result anyhow, so we could, in principle, delay the introduction of levels. That is, like, go and figure out a fixed point, and then what I would guess is at round k times 1024, I don't know, just a certain amount of time into the future that gives everyone 1024 rounds to start to figure their stuff out. Then throw in the levels negation, which absolutely does not interfere with the first k times 1024 rounds, and then shows up and says, "Hi, I'm here to make a problem. We need to make some modifications," but it leaves that prefix of the computation unmodified, which is great. It means that all of the changes that we will be working with, because they all derive from levels, right? The only thing that's changing coming into this iterative computation is levels. All those changes will go on the end of the list of changes to work on. We won't rederive anything that we've already derived. We'll just continue the derivation, essentially from where we left off. I wonder if that's actually easy to do. It's a little tricky because we have to crack open. We have to take levels into account to figure out what's the number in there. We don't otherwise know what round k we're talking about. So each record could, in levels, could be dot counted, and then dot delayed. Though that's a little weird because now we're as we increment the levels for a particular edge, we're changing the round in which it gets delayed to, which sort of interferes with a bit of computation. What we really want to do, just keep fantasizing further, is instead of just concatenating in more to advances to levels, I guess we could do that, but what we really want to do is to take levels, which has maybe a count of what would be like 27 for some edge, and smear out the negations over 27 different rounds. So if we do, if you have a count of 27, we might, at each multiple of 1024, some biggish number, up to 27, we subtract 1 from you. So each time we go and add a little bit more on, we don't change anything about the prefix. We just cause some more negations to show up, one more negation to show up a little bit later on, and that causes the computation to be a bit more stable. Again, to change a little bit less. But it's not immediately clear to me the right way to write that out. Hey, 800 seconds. So I think it was like 150 to, oh wait, our buffer isn't even long enough. I feel like it was 150 for the first thing, so like slower than the normal way to do things. And then our incremental update was just terrible. In part because we had to diff off of previous things. So the very first round didn't have to diff off of anything. Like, it didn't have any work to undo. And we had to, in some sense, undo all of that work and then redo it slightly differently. So if we had a clever way, I'm just going to think this through briefly. So levels has a bunch of edges with a bunch of counts. And we would love to change that into a bunch of diffs at different times, sort of delayed into the future, that I think I can write this as a timely data flow operator. I'm just a little worried that it's going to be terrifying. And so levels is a stream of triples, edge, comma, time, comma, plus or minus num. Yeah, okay, it's not as easy with the timely data flow thing, because if we count it, then it's sort of easy with a timely data flow operator. So let's try that. Actually, it's really not so hard, I don't think. We can try that, and then we'll see if it'll probably go up to 2,000 seconds to do this. But we're going to have a spread thing, which is going to spread out the. So levels is a collection. It has a stream in it. This is the timely data flow. I hope it has a stream in it. Inner, maybe? Jeez. Sorry, before we do that, we want to count it. We want to count it because otherwise what we'll see is a bunch of like edge +1. And we won't know it's a +1 from, so we don't know at what round we should. Oh, but we could look at the timestamp. Oh, wow. Oh my goodness. I'm about to write some really bad code that everyone should be very upset by. But let's see what happens. All right, we're not going to count things. We're just going to do this absolutely horribly. I mean, horribly, but like fun, right? Which is that this is a map. What comes in here? There's some data. It's an edge, edge, comma, time, comma, diff, and what we want to do is create a new one of these. We want to create a new edge time diff pair. But what we want to do, we're gonna absolutely cheat, and we are going to look at the round. So time should have the structure of. Well, we can sort of see things over here. A round, a k, and sorry, like a round of input, a k, and a round of active unrolling. So let's deconstruct that there. So input, I guess, k, and don't care. And we definitely don't care because we just brought it into the scope, so it should be 0 basically. So we really don't care. And what we're going to do is just change this to be something much simpler. Simpler? I don't know why I said that. Edge is simpler than you might have thought, maybe. Input, comma k, comma 1024 times k. Comma diff. Yep. And make this back into a collection. This is not the way any of you should be writing differential data flow programs. You should just have a slow program. I'm so sorry. This is too dangerous. So we're going to get the spread here. So what we're doing is we're taking in levels, which is telling us about the changes to the counts associated with each of the edges. And when we look at them, we'll be seeing something like an edge at some round of input and at some level k, probably got a +1. Like that's probably a pretty common change. You might see some minuses later in the computation. But all that we really want to say is that's wonderful. Let's hold off telling anyone about that until round 1024 times k. So we're just going to delay that information a little bit so that we don't disrupt the prior computation. And this is totally fine because what timely data flow underneath will say is like, all right, well, cool, I see your timestamp there. You happen, in round k, you all happen to be the earliest timestamps, 1024 times k, so I'll just leap directly to you. I won't reevaluate any of the earlier computation because no one has proposed any changes any earlier than 1024 times k. All right, hold on. Okay, we gotta add some using statements. I believe that. We need to add a few more few more methods. Is it just map? It's probably going to complain about as collection in just a moment. Must save the file. Yeah, good. Expected. Oh, sorry. Yeah, sorry. It's not a tuple. It is a timely order product thing. So let's see. This is fine. It's just sort of it's gross to type out. We have to use a different type other than tuple because tuple has its own opinions about less than or equals and stuff like that. And so we need to not use that. So let's actually just we can do a few things. Actually, I think we can possibly just do map in place, which and we'll call this time and what we need to do is set. We need some curly braces. Set time.inner, I think, equal to 1024 times time.inner, and some parenthesization and stuff like that. So this, or maybe not. What map in place lets us do is get mutable reference. So instead of having to deconstruct the thing and then build it back up again, we are presented with mutable references to the thing, and we get to run logic of our choice. And since all that we're doing is just overwriting one field, it's really not so painful. Let's see if Rust agrees that it's not so painful. No, it does not. So time dot outer. Sorry, time dot inner. I've just got the structure wrong in my head about what these things are. So time.inner is the innermost timestamp, and time.outer.inner is the, well, let's see if it builds first, and I'll tell you what I'm so sure it is. No method as collection, great. So time.outer is the pair of round of iteration and k, and time.inner is just that, the unraveling round. Sweet. All right. And this is absolutely correct. We didn't bother to mutate edge or diff, so we could totally have ignored them. We totally didn't need to include timely order product anymore. And we totally have a really unsafe, crazy program. I mean, not unsafe in the Rust sense, but kind of mental program that could plausibly go a little bit faster. So instead, what's going to happen in this inner loop here is we're going to have these spurts, 1024-ish long for each round k, where in each of them we do the appropriate unraveling to get us to the end of round k. And then sitting at k+1, we have a whole bunch of people who survived through round k, who now need to essentially have their counts decremented by 1 and determine if they should be admitted to. Well, they've all earned a place in k+1, but we now need to decrement their counts by 1 and see if they deserve to go on to k+2. But these spurts are now disjoint. Well, if 1024 were big enough, disjoint rounds of iteration, and pretty comfortable with the fact that even if they do overlap, we don't hit fixed point until we have included all of the updates. So previously they were all totally overlapping in the sense that all of these changes happened at moment 0 in this computation, which caused each of them to be massively overlapped, which meant they all changed any time the levels changed. And no matter how this works out, pretty sure we'll wind down with this, and I will go enjoy my weekend, and you can enjoy closing this window, and yeah. So you can see now, by the way, like these coordinates here are much larger, right? This is because we're leaping ahead 1,000 or so iterations in each of our rounds. And you might also notice, I think it's the case that although we're sort of taking longer steps as we go, we're not actually slowing down. We used to be slowing down as we went along. Because we had to revisit basically all these previous rounds of computation. So I think we're actually moving pretty fast now. We're gonna hit. I hope if this is still correct, hit 34. Yeah, 56 seconds, huh? It's pretty sweet. It's definitely faster than before. And now we're doing these modifications, and you can. The intent, at least, is that the modifications are in, kind of disjoint regions of time, and maybe not involve as much reworking. This is not 0.2 seconds, which was the sigma goal, but we might improve over 50 seconds, which was, or maybe not, 50 seconds, which is what we were getting with the optimistic version. Doesn't seem super fast, does it? This 10,000 element update seems slower. I guess it previously also was slower than the initial computation, which is stupid. That's annoying. Don't have a great intuitive understanding for that personally, but we're not going to take 800 seconds to finish this off, which is nice. Sweet. All right. Well, this was different. We went a lot faster in the initial computation, which was cool, but then our incremental update took substantially longer than we'd taken before. I'm gonna, just interested in terms of tidying up these numbers a bit, taking out like all these prints, which are consolidating all the things and definitely costing us some time, and possibly throwing in that reuse of active, just to try to get like a better measurement to end on. I'll start doing that. And so if you remember, when we do a thing multiple times, we can also just let active equals active dot arrange. In this case, arrange by self is the right one. When you're doing a semi-join, we don't have a we have to actually do join core active comma, and it doesn't really matter what we put here. We have to put something down. We still have to describe what do we do with our key and our value and that stuff. But I think the good news is we can copy and paste that several times for each of the semi-joins. Nope. All right. Let's see if that checks. Nope. Again, it's not clear this is a massive win because it's quite possibly still the case that active is not the large collection. It's actually the inputs to the join. And we would be delighted if we had a better incremental update rule than to just stash all of method arrange by self. No method names. Oh, poop. Okay, so we just need to change this to be something like. Cargo. That's awesome. Oh, wait, how? Stop. Wait, wait. This cargo check and cargo and check being put together unintentionally. All right, we're gonna build this thing. I'm gonna go stroll around for a little bit because I don't want to watch this any more than you do. But if you scrub forward a little bit in time, probably about 3 minutes, we'll be able to see what actually happened. All right, it's up and running. Previously, it was about 50 seconds, I think, to get going, then what, like 150 seconds to finish out, which is actually kind of backwards from the other implementation, right? Which took 100 seconds to get going, then 50 seconds. Sorry, 150 seconds to finished out. So we've moved the cost to the incremental updates, which sucks. All right, 40 seconds now instead of 50 something. Right? That's not a bad improvement. And then this might take a fair bit longer. Yeah, I really think there's some fundamental defect in the way I framed this, where incremental changes. So if we add some more edges in, yeah, it's not nearly as bad as it was before, right? Or am I misremembering that it was? I think I must have flushed it out, but I felt like it was sort of 50 seconds and 150, and this has been drawn down to sort of 65 or something, 66 second thing. It's just since it's done building. Let's throw out W2 on here. So the incremental update times are definitely worse than they used to be with the more weird algorithm. Even though we thought we were being pretty clever and doing less work. I mean, I guess we had no particular reason to believe that this is any better. We're definitely not doing the same things that the paper proposed, not even the simple same things. The intent was to unpeel, oh, that's nice. The intent was to unpeel these layers in a different direction, but we don't exactly have access to these like the priority queue type structures that let them avoid doing quite a lot of work that we're doing. Or our brains would have to become more powerful to figure out exactly how that works. 26 seconds is definitely better than the startup time for the optimistic algorithm. I guess this algorithm is the pessimistic algorithm. I'll give it that name. Yeah, so what is that? That's 45 instead of 65 seconds. Yeah, that's not so bad for a second thread. I'll be curious to see how this runs on the desktop. I'll try to check that out. My guess is better, but not. It's not going to fundamentally change the balance of running times here, which is much more in the incremental update time than in the startup time. But let's stop there for now. I'm tempted to put copy a source main over to pessimistic.rs. Yeah, right, clever. Main to source bin. Great. All right. Well, I'm gonna stop there then, and I think one of the points of this was to try to assess whether assess. I don't know, if, like, to be insufferable and try to see if, given sort of a fair challenge, these existing algorithms, so UnitSim, like this sort of recent awesome one, and XH, the prior work state of the art, like how they sort of rated to, I was going to say a more dumb approach, but like taking something like differential dataflow and just writing the algorithm as you might write it and seeing how it works. And I don't know, I think we can draw different conclusions, but my guess is, my sort of sense is that this is absolutely much faster. The XH algorithm, whatever that is, seems kind of comparable, to be honest. It's a bit of a, it depends which way we do things, and we're using lots and lots of memory compared to them. You might notice that XH's index creation day at 0, so it does no work, I think, before it starts running. So this in no sense is differential data flow rendering these things irrelevant. Actually, they're substantially better than it in many dimensions. Though this took us all of a few hours, I suppose, to sort of put together and assess. Much of which was compiling, actually, so this could have been even faster with some speeded up tools. And plausibly, we might be able to improve this a little bit more if we think a bit more deeply about why was it slow to do certain, like why is the incremental updating as slow as it is. Maybe I'll be able to get my brain around that and tweak the code in some pleasant way that makes both the pessimistic algorithm's initial computation fast and its incremental update time proportionately faster. Maybe not, but yeah, I hope it's been a pleasure for you as well. I'll be back at some point in the future, possibly with some different graph computations. I have a request to put together some simpler ones. We'll try that out.